So Jamie did this beautiful 3D model that you see the soma and the nucleus and the dendrites and the myelin sheath. Looks like these crystals. It's very nice. This one was a cake that was baked with this amazing neuron frosting on top. That's excellent. So next we're turning our attention to the communication factor of neurons, because that's what they're supposed to do. They're supposed to communicate information. And we can talk about sort of hardware and wetware in terms of the body. We've got electrical information that's going to be passed, but we also have chemical information that's going to be passed. And in this chapter we're talking about the electrical signals, and in the next chapter we're going to be talking about the chemical signals. So a nerve impulse is that electrical message that's going to go down the length of an axon. And this axon, remember, it's made up of that bilipid level, very thin membrane, and this electrical message, this charge, is going to recalibrate or repropagate, regenerate at every little piece of that cell all the way down the axon. And the speed of this nerve impulse goes from 1 meter per second to 100 meters per second, so it can go very quickly. The resting potential of the neuron is important because the cell expends a lot of energy between nerve impulses of maintaining a hyperpolarized charge. So generally it's on average, it depends on the cell. Some places talk about negative 60 millivolts, some negative 50, generally you see negative 70 millivolts. And that cell is maintaining this higher negativity on the inside by pushing out, spending energy to keep sodium, the chemical transcription is Na, keeping sodium outside. And when a nerve signal is going to be passed along, those protein channels open up and allow those ions to come in. So you can have this pulse. And the other chemical ion that's important is potassium, which is K. Now, how these electrical impulses are measured is with a microelectrode, this tiny little, they used to be glass tubules that you could insert into the cell and record what was going on. And typically the cell that was used was called the giant axon that was found in the squid that went from its mantle to the tentacle. And these were visible. You could see these, and you could make sure you were inserting the microelectrode appropriately. The microelectrodes that are measuring electrical current are sent to an amplifier, so these are boosted basically, and then that signal is sent nowadays to a computer, and you can see an oscillogram, this graphic of what's going on. In this second schematic you can see an image of the microtubule going in, and that's been magnified hundreds of times. So very interesting. What I'd like to do is give you a quick recording with both the sound and the visual. It's kind of funny. It sounds almost like some kind of rapid old typewriter or something, but I really wanted you to get that experience. It's amazing because that burst is a bunch of nerve impulses being sent. And you could see what it looks like when they're recording that. And I was at that website. Okay. So this is a depiction of that real-time capture that you just saw. And it's showing the waveform itself from the negative 70 millivolts, crossing that threshold, to about a positive 40 millivolts, and then the gate shutting, and the decrease, which one nerve impulse lasts about 1 millisecond. One of the things you'll want to notice about this curve is that it goes below where it started, and that means that you can't get back propagation. You can't wash the signal backwards. It's always going in one direction forward down the axon away from the body. It can't back up, can't go backwards, because this is even more negative, so it can't spike up. And so one of the things they're looking at is the rate of firing. And for most cells, there's a spontaneous firing rate, so it's always sort of firing little bursts, and trying to see if there are changes in the intensity of that firing. And this is interesting because it's looking at the firing rates on the optic nerve, and what they've done is they're increasing the light intensity. So you've got the light on, so you see the firing goes up, but you get higher intensity light, and then with the highest intensity light, and you see the number of spikes from the dimmer light to the most intense is much faster. So the signal is saying it's brighter, 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 brighter until the light goes off. So again, at rest, there's a more negative electrical charge maintained, and this resting potential is important to maintain that tension and allow that progression to be ready whenever it's needed. I'm giving an example of, like, if you're going to shoot an arrow and you pull the bow back and you're ready and you're just waiting to release, versus if something's coming and you wanted to send that arrow out and then you had to pull back the bow and then release it, you'd lose a lot of time. Okay, so we've got all these different ions that are interacting with their different charges. Sodium, potassium, calcium, and chloride are going through different channels in the membrane. And there's a sodium-potassium pump, and it maintains this 3 sodium ions out of the cell while drawing 2 potassium ions in the cell to maintain that gradient. And here's kind of a depiction. The pump is those protein channels. And so once the neuron is stimulated, going from that hyperpolarized point to depolarizing, so there's enough of a charge to send a signal, and it hits that threshold of excitement. Hopefully we've got, where it crosses a threshold where the signal is going to be sent no matter what, and it's called an all or none signal. Like, it doesn't get sent partially, it goes all the way. And the voltage activated channels are going to engage and allow the sodium ions to rush in, changing the electrical radiance. So now it's much more positive. Remember, it shoots up to about maybe a positive 40 millivolts. And this is just showing. And here you see that even more hyperpolarization. This is a nice website that is showing the action potential as well as the sodium channel. And you can see those in an animated form. So here's where I would say stop and take a look at that. Seriously, do stop and go to that site.